Let's discuss a theorem in calculus that is fairly intuitive to understand, but sometimes more difficult to actually apply in the context of a problem. And that theorem is called the squeeze theorem. You can see by this graph I've drawn that I'm considering three functions here. H of x, which lies entirely beneath g of x, which lies entirely beneath f of x, for some open interval containing the x-coordinate a. Furthermore, the limit as x approaches a of f of x is the same as the limit as x approaches a of h of x, which is equal to this y value of L. And if those two things are true, then our conclusion is that the limit as x approaches a of g of x is also equal to L. In a way, g of x is squeezed between f and h. This theorem is sometimes also referred to as the sandwich theorem for the same reason. Now let's take a look at how to apply this theorem in the context of an AP problem. I've pulled here the stem of an AP problem, and actually we only need the first sentence of the stem, so we can kind of ignore this part. This part was relevant in the other parts of the problem, but not so much in part D, which we're going to talk about here. It tells us that the functions f, g, and h are twice differentiable. It's very important language there, and that g of 2 and h of 2 are both equal to 4. In part D, we are then presented with a third function, k, and we are told that k lies entirely between g and h. This is a very common inequality that you're going to be given when you know it's time to apply the squeeze theorem. Now, what are we asked to do in this problem? We're asked to conclude whether or not k is continuous at x equals 2 and justify our answer. Now, continuity is the other important piece of this, so let's remind ourselves of the definition of continuity. In order for k to be continuous at 2, k of 2 must exist. The limit as x approaches 2 of k of x must exist. And the third component is that these two are equal to one another. If those three conditions are met, then we can conclude that k is continuous at x equals 2. So let's start with the first condition. Can we prove that k of 2 exists? Well, in order to do that, let's remember what we were given. We were told that g of 2 and h of 2 are both equal to 4, and furthermore, we were told that k of x lies in between g of x and h of x on the interval from 1 to 3. It is then natural to conclude that k of 2 lies between g of 2 and h of 2 on that interval. And since these outside values were given to be 4, then k of 2 is squeezed in between the others and will also have a value of 4. So our first condition is met. The second condition takes a little bit more of a leap to get to. We need to address whether or not the limit as x approaches 2 of k of x exists. For that, we're going to have to go back and analyze this statement right here. What does it mean for a function to be twice differentiable? Well, differentiability implies continuity. And so if g and h are both differentiable, then they are also both continuous. And if g and h are both continuous at 2, well then not only must their function values be equal to 4, but their limits must be equal to 4. So the limit as x approaches 2 of g of x must be 4, because that's g of 2, and the limit as x approaches 2 of h of x must also be 4. Now remember what the squeeze theorem says. Provided we have this third function that lies entirely between the other two, and provided the limit of the outer two functions are both equal to some value L, then the squeeze theorem guarantees us that the limit of the interior function must also be equal to L. So we can say by the squeeze theorem, the limit as x approaches 2 of k of x also equals 4. Therefore, we can check that off the list as well. Finally, we need to show that they are equal, and we can do that in our concluding statement. So our conclusion is going to be that k is continuous at x equals 2 because k of 2, which is equal to 4, is also equal to the limit as x approaches 2 of k of x.